In this video, we're going to discuss mechanisms of reactions. How does a reaction actually occur at the molecular level? So while we may have a balanced reaction that shows how much of a starting material we need, how much products we're going to make, this doesn't tell us anything about the path we took to get there. How is it that our molecules rearrange in this fashion? Well, we can imagine a couple things. Hey, it says I need two starting materials. Does that mean two of them have to be involved in interacting with each other? Maybe. We could imagine a situation where I have a nitrogen with a chlorine, oxygen, oxygen, and I have a second one. We have our two starting materials, the two NO2Cls. These bounce all around our container, but just the right angle, it's possible that you could smash those chlorines together. And if you hit just hard enough, they might squish into each other and break the bonds. You'd shatter the existing NCl bond, the chlorines would stick to each other, these would bounce off, and when they broke off, the NCls would break, your ClCls would stick together, and your NOs would still be attached. In doing so, we've made our products. I have two NO2s, I have a Cl2. This is one way this reaction could occur. So this is the idea of the mechanism. We've proposed the idea that two starting material molecules must impact breaking the chlorine atoms off together at the same time. When we talk about individual steps, we call them elementary steps. An elementary step is a single proposed interaction and the result of it. It may or may not look like a balanced reaction. In this case, it does. We are proposing that this is exactly what happens in one step. Two of our starting molecules come together and simultaneously shatter in such a way as to make two NO2s and a Cl2. Well, elementary steps have their own rate laws. Basically, there's a K times the concentration of reactants to the order of the number of that reactant in the step. So in this case, the rate of this step would equal some K. Well, the only molecules that interacted as reactants were two NO2Cls. And because there were two of them, it would be to the second power. What we proposed was a second order reaction. Why would it be second order? Well, it's got to find another of itself. If I had a container and there's very little of these molecules, each of them is moving around trying to run into another of the molecule. They'll eventually find each other. But if there were more X's, well, then the chances of any of these running into something eventually goes up. They're just more likely to run into another starting material if there's more of them. And each of them is more likely. The net effect is, hey, if I've got 2 of something versus 4 of something, well, I had one possible interaction to start, but now I've got 4 possible interactions. Doubling my stuff, going from 2 to 4 X's there, quadrupled my opportunities. And so if doubling your stuff quadruples your rate, that's second order. So that's what we see occurring here. Now, this is our proposed mechanism. However, well, you can only really know the rate if you test it experimentally. Your balanced reaction cannot tell you your rate law. That was emphasized before because the real rate law, when we experimentally determine it, is K NO2Cl to the first. It's a first order reaction. So while we proposed this idea of two starting materials colliding and breaking into products, if that was the case, it should be second order in respect to starting material. It's not, it's first order. This tells us that this cannot be our mechanism. The reaction cannot go through this path. It can't just have two starting materials collide, sticking the chlorines together. Something else must instead be occurring. In which case, we have to think about other things. It can't be the reaction we already proposed. So what else could happen? Well, especially because, hey, it's first order and starting material, and you got to do something with your starting material. Let's imagine I have just one of my starting materials. So instead of two of them colliding, maybe this just breaks. Maybe we get our NO compound and a radical chlorine. Maybe that NCl bond just breaks. Instead of sticking two chlorines together, maybe it just gets hit in a collision hard enough to shatter. An NCl bond isn't all that strong, and so it's not unreasonable to think that it could break. Well, now I've got these floating around in a container. So originally I had a container, it just had starting material. One of these broke apart into product and Cl dot. Well, we probably had lots of starting material originally, so this has just occurred. We've just made a little NO2 and Cl radical. Well, I need more NO2. I'm supposed to make two in my reaction. Remember, it's two starting materials turned into two NO2s and a Cl2. I've made one of my NO2s, and I got rid of one of my starting material. I have not yet made Cl2, so I got to do some other stuff. Reaction 2. Well, I need to use up more starting material, so let's say I have another starting material. And, well, my product has already been made, so I probably don't need to use that NO2 necessarily, but Cl dot is not a product. It needs to do something and go away. So what if it reacted? What could happen here? Well, a radical is very reactive. It's actually really good at cutting a bond. It'll stick to one of the things and leave the other thing as a radical, which, hey, that's what NO2 already is. So why doesn't this radical chlorine break that bond, make the radical N, and bond to the chlorine? We could get our Cl2 and another NO2. This means if we were to sum our reactions kind of Hess-Law style, I've got two starting materials on the left. That matches. I've got two product NO2s on the right and a Cl2 on the right. Our Cl dot got canceled because it's on both sides. And so the sum of these steps actually does add up to the overall reaction. So we can imagine these individual steps as sort of a Hess law. How that goes on to affect our rate, however, depends on which of these steps is faster. Real rates include everything up to and including the slow step. What do we mean by that? Well, imagine you're getting something shipped. There's a giant warehouse, and there's some trucks, and Amazon drives them, and it brings them to your house. So you got a smaller house here, and they drop a package off. And that's off to go and do another delivery to another place, and maybe UPS comes in and also drops a package. Well, until they're in your home, you haven't really opened it and received whatever it is. If whatever's inside the package is the product in this idea, getting it shipped to you, it could get slowed down at a warehouse, it could get slowed down on the road, or it could get slowed down on your porch, waiting for you to bring it inside. depending on where is slow in here, you will pile up material, but after that step, it goes much faster. If you order 1,000 things and Amazon's what's being slow, then you'll get 1 or 2 packages at a time. And so the speed at which you can get them in your home, well, every day you'll come home, there'll be 2 or 3, but they won't all be there. It's the delivery that's the slow point. On the other hand, if Amazon's really good and can just pile up all your packages and you not being home is the slowdown, well, then they won't really reach the product until you come home to bring them inside. Where the slow step is determines where things pile up. The net effect on this is that material after the slow step never appears in quantities great enough by comparison to really be noticeable. And so if the first step was slow, well, we'd have to come up with a rate for each elementary step. So before even figuring out which is slow, we could say the first one would be equal to K times, well, we have one starting molecule, so NO2Cl to the first power. The second step involves 2 things. It has some other K, it has one starting molecule, but it also has one Cl radical. Well, our real rate law is just dependent on the concentration of starting material to the first power, and that looks very much like the first step. Our rates are dependent on the mechanism that's being followed and which step in the mechanism is slow. I can have a graph. I have a lot of starting NO2Cls. I can make some Cl dot. I can make some Cl2. And we'll start with a whole bunch of starting material. After a little bit of time, some of it reacts and we make a little Cl dot. And we wait. It's a little bit of time, but in the meantime, if the next step is faster, boom, that Cl dot becomes Cl2. And then we wait for a little while, and there's some more starting material reacts, which makes a little bit more Cl dot, but then right away, boom, that moves over to Cl2. If Cl2 is just faster at forming, if the second step is faster than the first step, well then, as we're watching and time's ticking on and we're waiting and waiting and waiting, the next bit of Cl2 is only going to show up when some Cl shows up. This is the idea of a rate limiting step. The rate at which our Cl2 can accumulate is dependent on the earlier step of Cl dot showing up. If, on the other hand, our second step was the slow one, well, then the idea is I'd make some Cl dot, and then I'd probably make a little bit more Cl dot before any made product. But it wouldn't use up all my Cl dot because, well, I'm forming Cl dot faster than I'm making the Cl2 in that case. And so we'd keep making some more of this. A little bit of it would transfer. We'd keep making some more of it. What we'd see is that it would start to pile up. We'd see both species. So that was if the second step was slow. Eventually, we'd use up all our starting material. And then at that point, bit by bit, we'd move our Cl dot over to Cl2. And eventually, we'd reach product. And so whether you ever see an accumulation of the Cl dot depends on if the first step was slow in making it, and then any that appeared immediately got used in the second step, or if the second step was slow, allowing you to build up some Cl dot because it wasn't going away very quickly. Well, this affects our rate. And since the real rate looks like the first step, we can safely assume that the first step must be the slow step. This doesn't mean that this is the actual mechanism. We really can't follow individual molecules and observe them. Rate laws gives us the ability to rule out certain reactions, like our original one where 2 starting materials impact and create all 3 products. and they can strongly suggest an idea is correct. However, we can't really watch this to see this occur. There are tricks that can be done. You can put in things that would react with radical chlorine really well, and so you might be able to spot if radical chlorine actually ever shows up as an intermediate. However, there's a lot of work that goes into that kind of testing. In just theorizing what our reactions could be, though, we do find that this is a legitimate possibility. If our first step leads to our second step and our first step is slow, then we would have the correct rate law observed. What happens if your second step is the slow one, and how does that affect your rate law, as it would force you to then combine all the steps up to and including the slow step? Well, we'll see that in another video. But this is the idea of individual elementary steps of a mechanism. Bit by bit, how do our molecules break down, rearrange to form our products, and how would that affect our rate?